So when you draw the steel portion of the iron carbon diagram, remember we are going to have our temperature axis, temperature on the y-axis, and then our percent weight carbon on the x-axis. And remember we are going to have our utectic temperature, which is on 723, and then we are going to have our 910 degrees Celsius here. So with this now, can draw this line, join this together to this, and then I take my utectic point up. Right. Remember that this region is our 0.8% region, and this is our 0.02 weight percent of carbon. Right. Now, anything above 910 degrees Celsius, you have stable austenite. Right. We have stable austenite, and then here we have alpha phase. Okay. Now you see this region and this region, both alpha and austenite, they are sharing boundary. So in this place, I will write alpha plus austenite. So I think that's cool. Right. One thing I would like us to know is that any steel that is within the range of 0.8, that is less than 0.8, we call that steel hypoutectoid steel. Call it hypoutectoid steel. And any steel that is above 0.8, we call that steel hyperutectoid steel. Okay, so this is just the difference between hypoutectoid and hyperutectoid. One is having carbon content less than 0.8, and the other is having carbon content above 0.8. Now, if you cool this austenite through this utectoid point, you are going to have alpha plus Fe3C, which is cementite. Now, if you look at this reaction that is alpha transforming, ferrite, austenite transforming into alpha plus Fe3C. You might be asked, what is the name of this transformation? First, this transformation is called utectoid transformation. Utectoid transformation. Let me just put it somewhere around here. Utectoid transformation. And this transformation occurs at 723 degrees Celsius. So, what this phase diagram was able to tell us is what will be the transformation of austenite when it is being cooled through this utectoid point. Of course, it tells us that at 723 degrees Celsius, when we cool down austenite, we are going to have alpha plus ferrite, alpha plus cementite. But this phase diagram does not tell us for how long. And in industry, we need time. In industry, time is the most challenging factor, and that is why in industry, this iron carbon diagram is not as important, is not in capital letter, not as important, is not as important as our TTT curve. And what is the TTT curve? TTT curve is time temperature transformation. Now, if this phase diagram will be able to tell us what will be the next phase, or what will be the transformation of austenite at 723 when we cool down, we are going to have ferrite plus cementite, which you call them perlite. Perlite is a lamellar structure of combination of alpha and cementite. So when you cool down austenite at 723, you are going to have perlite. But for how long? We don't know. That is why we will now introduce what we call our TTT curve. So what is the TTT curve? TTT curve is time temperature transformation curve. That is to say, this curve is dependent on both time and temperature. Now let me just quickly draw this again. Okay, you remember this temperature 723, remember this 910 degrees Celsius. This is our authoritative point. Then we raise it up. This is 0.8, right? Let me just write it. This is 0.02. This is austenite, and this is alpha plus austenite, and this is alpha. Now, in the ion carbon diagram, there is what we call critical temperatures. Okay, there is critical temperature. Now, this line, authoritative line, is critical temperature of A1. Call it A1. Why this line that separates the region of single phase and that two phase is called A3 critical temperature. Now from here I can extend this line outward. Let me extend it outward. Let me extend this A1 outward. Then if I do that, let me just draw a line here. So this TTT curve, it's a curve of temperature against log of time. Okay, against what? Log of time, so that it can capture all the transformation in any time. Here I will extend this A3 line, and I will also extend this A1 line. Then here I will have another line down here, and I'll have another line as well down here. So this line is our A3 line, this line is our A1 line. This is, let me change pen, so that this line is our MS, meaning martensite start, and this last one is our MF, meaning martensite finish. Now, just like this time temperature transformation curve, it can also be called the C curve, or you can call it isothermal, that is constant temperature. So if you draw something like this, and then I draw the other one like this. So this is our CC curve, this is our TTT curve, or C curve, or isothermal curve. Now this A3, remember that in this region above 910 degrees Celsius we have austenite, and austenite is stable, so I will have austenite here. But this austenite is very stable, remember, because it is not undergoing any transformation. At this temperature it is very stable, and below this temperature austenite is not stable. That is to say, above A3 austenite is stable, and below A3 austenite is unstable. So here I can have unstable austenite, unstable gamma. Now